Hello, it's Keith here, and this is lesson 3 of the so-called Min series of my Z80 assembly programming tutorials. We're looking at my minimum tile map example. So basically we've got an example here on the ZX Spectrum. It works on all the other systems as well, but this is the ZX Spectrum version. And what we've got is we've got this tile map, which is the background, of course, but we can also use the tile map to simulate sprites. And so we've got our Chibico character here. And as our Chibico character moves around the screen, obviously when we redraw that character somewhere else, we're going to need to redraw the background underneath, because this is the ZX Spectrum, it's a bitmap screen, and we don't use a double buffer, which is why you can see we've got some flickering. We also are going to have a look at the scrolling code today, because you can see we have a basic scrolling function which allows us to scroll up to 4 tiles. The physical tile map is 36 tiles, the visible tile map is 32 tiles. So we've got a small scrolling area, and we're going to look at the code that handles that and optimizes that. Whenever a change is required to the screen, something known as the tile cache is updated. A value that's non-zero in that is a tile that needs to be drawn. A value of 0 is simply nothing is done. And so by optimizing our changes, we can increase the speed of the drawing and reduce the flickering, because as I say, there is no double buffer with regards to our drawing here. So that is what we are going to look at today. Okay, well, let's get rid of this and let's have a look at the code. Okay, over we go. Okay, so we're going to be looking at the minimum tile map code, and the first thing we're going to be looking at is the remove sprite routine. So this is going to take the sprite off the screen and draw the background where the sprite used to be. So the first thing we're doing here is we're checking the refresh tile tag flag and seeing if that is non-zero. If it is non-zero, then we do need to do the refresh, otherwise the sprite presumably hasn't moved. So the first thing we're doing here is we're getting the old position of the sprite, because we're assuming the sprite might have moved here. And we've got these low res functions. Basically, MinTile can work in movements of up to, with precision of up to 2 pixel movements, but the code isn't really optimized for that. It's a crude tile map, and smooth movements tend to cause glitches with partially empty sprites if they're partially transparent. So to simplify things, we can use low res coordinates, which convert the logical units into a number of tiles. There's 2 pixels per logical unit. That means 4 logical units per tile. So we're rounding to a number of tiles here, and that fixes the glitches but makes the movement a little jerkier. We're then loading in the old width if we have it, otherwise we're loading in the current width and height. And then we are doing our cropping routine to calculate the position of the tile map that needs to be drawn. Now, in the case that our sprite is partially off the screen, the amount of tile map we're going to draw is going to need to be altered accordingly, and so we're doing that. But we don't need to worry about cropping in this case, because whatever the flipping of the sprite, we're not going to do anything like that with regards to the tile map. We've then got a simple routine here called do crop logical to tile, and all this does is it converts the x, y, width and height into a number of tiles, and if that is 0, if any of those have resulted in a 0 width or height, then we're going to return. Otherwise, we're actually going to do our draw. So what we're doing here is we've loaded the width and height into IX here. We're loading the width of our tile map cache, which is 32 tiles, into IYH, and the destination into DE here. Now this will shift the DE tile map to take into account our X and Y coordinate, because if our sprite is in the middle of the screen, the area of the tile map we're going to want to draw is only that middle screen area. We don't want to redraw the rest, so we are going to shift our DE destination to take into account that start position of our actual sprite that we need to remove. What we're then going to do is we're then going to load our background tile map. This is the source tiles that we want to replace it with into DE. We're going to add the scrolling offset here. The bottom 2 bits are the partial offset, because with 2 bits because the actual tile map is 36 tiles, but only 32 of them are visible. So there's 0, 1, 2 or 3 offset to that tile map, so that's why we're using just 2 bits of that, and we are adding that offset, and then we're shifting that source tile map. So here we're shifting the source tile map, here we're shifting the destination cache, and so now both have been offset relative to the position of the sprite. So we're now ready to actually transfer our data. Now we're loading the actual width of the tile map, which is 32 tiles. That's the tile cache, that is, sorry. And so what we're going to do is we're basically going to transfer all of the tiles from tile map 2 into the tile cache according to the width and height of our sprite. And so that's what we're doing here. We're going to use LDIR to transfer each line of our sprite that needs to be replaced. So we're selecting the width of our sprite here, and we're transferring the BC bytes, B being 0 here. So we're transferring basically C bytes, which is the width of our sprite, from the tile map to the tile cache, and that is replacing the old position of the sprite with the original tiles. So we're basically doing that here. We're then basically moving down the source tile map by one full strip here. We're moving down one full tile map width in our destination tile map here. We're then moving down one full tile map in our source tile map here. So we've got that in IYH here. And we're then repeating for all the remaining lines of the height of the sprite that we're trying to remove. So this is via the LDIR, updating the tile cache with the original tiles that need to be drawn to remove that sprite from the screen. It's a little bit weird, I know, but as I say, basically this will do that for us. Now this is being helped out by a few functions here, like this shift tile map function and this do logical to tile. We're going to see those now. Now the shift tile map function is basically just taking into account that if we've got a tile map and we have passed it 0, 0 and we want to remove this sprite here, we need to move that memory address across to the X position and then down to the Y position for the top corner of our sprite. That's what's going to happen here. Basically here we are taking the tile map width of the tile map that we need to offset and loading that into E here. D is loaded with 0. And we're going to repeatedly add that for each line. So this is a simple multiplication, basically multiplying the width of the tile map by the Y position of our sprite. And that's moving the DE address that was passed to us for the tile map to offset it to the first line here. We're then adding the X position of the sprite here, and that's moving the memory address offset by the X position. And so when this returns, HL will point to the top corner tile that is defined by the BC XY coordinate that we passed. And so that's being used here to select the offset for the first tile in our source, and here for the first tile of our destination cache here. So that's how that is used. Do crop logical to tile is a simple routine. Our logical coordinates use 4 logical units per tile. So to convert those to tiles, all we're doing is dividing our X position, our Y position, our width and our height by 4. Now the problem with that is, of course, if we had a width of 3 and we've divided that by 4, then that will effectively become below 0. And so we're checking if the width and or the height have become 0, and we're returning if either has become 0. And so when this is executed, it will return with the 0 flag set if the sprite shouldn't be drawn, if there's nothing to draw, if the height 0 or the width is 0, or of course both are 0. Now the last routine we're going to see here is the change scroll routine. Now, as I said before, we can basically scroll just by pressing the fire button here. We are scrolling our background tile map. Now on the master system we've got a hardware tile map, so that's very fast, but on a system like the Amstrad CPC with its big 16K screen, or 12K in the resolution I'm using, but its big screen means that drawing tiles is a bit of a pain. So we don't want to draw any more tiles than required. Now the scrolling routine always scrolls in one full tile blocks, and so we might have 2 tiles next to each other that are the same tile, and so as we've scrolled by one tile, a lot of those coordinates may actually still be showing the exact same tile they were before, and so we don't want to redraw those because we'd just be redrawing what's already there. So the change scroll routine can be passed 2 tile maps, and it will compare the 2 and see if they are both the same, and if they're both the same, it will not change the cache. If they're different, it will update the cache and say that tile needs to be redrawn. So that's what's being done here. So BC and HL are our source tile maps. These need to be 36 tiles wide, so 24 in hexadecimal. The reason for that is, as I say, is the background tile map, which is the source data, is always bigger than the screen by 4 tiles, so 36. But the cache is only 32 tiles wide because that's the size of the visible screen. So what we're going to do here is we're going to compare those 2 tile maps. If they're the same, we do nothing. If they're different, then we're writing the tile into DE. So that is saying that the tile in the BC tile map needs to be redrawn to the screen. We're then increasing all of the coordinates for the 3 tile maps, the 2 source ones being compared and the destination one, and we're repeating for each line of the screen. Now once we've done a full line, basically we are skipping the 4 unused tiles within the background tile map. As I say, it's 36 tiles, but the screen's only 32, so there's 4 tiles we need to skip. We're skipping those here, and we're repeating for the next line. And so that's how that routine works. Now, there's one part that we've not discussed yet, and we're going to discuss that next time because it's a little bit complicated. Zero sprite in cache. Now, as we move our sprite around, and we're redrawing the tiles where the sprite was and then drawing it back on the screen where it is again now. But as I say, we've got no double buffer. That was one of the requirements of this code. I wanted to work without a double buffer. And that means that redrawing lots of the screen is going to be flickery. And so what I do is I work out if the old position of the sprite and the new position of the sprite are partially overlapping, well, we need to only redraw the part that is actually not being overlapped by the new sprite. And so that is what the zero sprite in cache routine does. It compares the two positions and sees where the overlap is, and it zeros those in the cache so they won't be redrawn. And that's why if you see the code, when the sprite moves, only the edges flicker, because that's only the area that it's been having to redraw. Unfortunately though, that's also why this code is partially glitchy with irregular shaped sprites which have transparent areas. As I say, it's a basic tile map. The max tile routine that I'm working on will be better. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.